From HanselMinutes.com, it's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 280, recorded live Thursday, August 18th, 2011. Support for Hansel Minutes is provided by Telerik RAD Controls, the most comprehensive suite of components for Windows Forms and ASP.NET web applications. Online at www.telerik.com. In this episode, Scott talks with Haixun Wang from Microsoft Research Asia about Trinity.
Hi, this is Scott Hanselman, and this is another episode of Hansel Minutes. And today, I am Skyped in with Haixun Wang from Microsoft Research Asia, calling in all the way from China right now.
Yes.
Fantastic. Thank you for taking the time to chat with me. I wanted to talk to you about your project called Trinity. And you do a lot of work in Microsoft Research, and you've got a number of projects. You've got Trinity, one called WebQ, and Probase. But Trinity is a data structure that thinks about things in terms of a graph. Give me some background on what Trinity is.
Well, Trinity is actually two projects. Trinity first is a graph database, which handles very, very large graph structures, and support online query processing. It's just like a database which answers queries posed by the users. And on the other hand, Trinity is also a graph computation platform for offline large analytics. So if you want to do very, very large jobs on graph data, and it's just like what you would do for text data or other kinds of data using, for example, MapReduce mechanism, you can use Trinity to process very large data in an offline manner.
Okay. So for a developer who might be listening who is familiar with object relational data or document databases, like Mongo, what is a graph database?
The graph database is special in the sense that it makes the graph exploration much easier than traditional database. So you can use traditional database, for example, relational database, to support graph data. But then you run into a very, very big problem, which is graph exploration will correspond to join operations on the underlying data, and the join is a very, very expensive operation. Usually for graph data, you would like to explore the graph, freely, and then each exploration, every step you want to explore will correspond to a join operation. So relational database apparently cannot handle that. And the current other NoSQL approach, including, for example, Hadoop and other key value paired stores, they won't be able to do that as well because they cannot handle that many joins when they want to process the queries in an online fashion. So graph database is just special. I mean, it supports online graph exploration without using joins. That's the most important thing to know about the graph database.
Okay, so let me think if I understand this correctly, because I do not have a PhD, and I'm not sure how many of our listeners do. I know that when I've given interview questions before, I've asked junior engineers to say, can you express a tree structure in an object relational database? And often very beginner people will make multiple tables, and then a more advanced person will make a tree structure that's a single self-referential table. And then the tree structure becomes extremely complex as the joins to the table itself kind of start to recurse, and it becomes pretty hairy to make these kind of infinitely deep self-referential tables. Is that what you're describing to the trouble in creating a graph in an object relational manner?
Yes. So imagine you want to, for example, represent a tree or a graph using, multiple tables or a single table with self-referencing pointers. So basically what you are doing is that you are using keys to reference, for example, the neighbors of a particular node or the child nodes of a parent node in a tree structure.
Mm-hmm.
So in order to find your child nodes or your neighbors in a graph, you basically need to search through those keys, right? You need to use an index structure to help you to find those keys immediately, and then you will retrieve those records from the database, from the table, and then you find your neighbors or your child nodes. So you need to go through this process. So this is going to be very, very slow because basically you are accessing the index and you are doing a join operation. So by doing a join operation, I mean those values are not connected directly. You need to go through the index. So a graph database can be defined, as it can find its neighbors or its child nodes without using the index. If a database system can do that, then we can call it a native graph database system. Otherwise, it's just using, for example, multiple tables or relational database to simulate a graph database.
I see. So would it be fair to say that often people have data that is graph in shape, and then they use the database that they're the most comfortable with and begin to run into trouble? And this is kind of a specific kind of database for a specific kind of data.
Yes. So of course, a lot of transaction data, they are not really in the form of a graph, but more and more applications right now, they are working on very complex data, and this kind of data is can be nicely represented by graphs because graphs have a lot of flexibility in representing those kind of structures. And just like you said, people would naturally use traditional data management systems, key value stores or relational database to support these kind of new applications. And whenever the data gets larger and the operations get more complex, they will run into problems where response time is just not too long for their online query processing.
Mm-hmm. And if I were to create a naive in-memory graph structure myself, and maybe I said I'm going to have a database of a couple gigabytes in memory, and I'll make just a big giant bunch of C# objects, what kinds of issues would I run into with a naive implementation that would be solved by a formal implementation like Trinity?
So basically, first of all, you would need the data structure to be stored in memory because typically the graph data does not have locality, which means you cannot really use sequential access to get your information. Usually, your nodes, the neighbors of a particular node, they are all over the place. So you would like all those kind of information reside in the memory, in the main memory instead of on the disk, right? So if you only have a small graph, then you can do that using all kinds of, the runtime structures to manage your graph. That is fine. Mm-hmm. But usually we need to handle very, very large graphs. So many applications, they need to handle very large graphs like, a social network, or in bioinformatics, you need to handle the gene sequence of a human being. And those kind of data, you cannot use a single machine to support it because it's just the memory is not enough, right? Mm-hmm. And then one approach actually used by a lot of current application is that they are buying a very, very powerful machine which can have up to say 1 terabyte of memory. So this is sort of the the approach people are taking right now. But of course, those machines are very costly, and it still has the scalability problem because data is getting larger and larger. So that's the major challenge. And for example, if you imagine a large social network like Facebook, right? So Facebook has probably close to 1 billion, let's say 800 million users, and for each user on average, you have like 150 friends. So for such a graph, we are talking about over 1 terabyte of information just to represent the graph topology. Okay, nothing else, just the graph topology. So you probably cannot use a single machine to do that. And even if you can, a single machine probably does not have that much parallel capability to support so many concurrent online operations. So you want to scale out the system into, for example, a cluster of 50 machines or 200 machines or things like that. And that is actually what we are doing. We are providing this scalability through a cluster of maybe hundreds or even thousands of machines to support applications at the same time, many concurrent operations at the same time. So and in this way, of course, we can support very, very large graphs. So we can support, for example, the entire web graph, which will take probably 300 to 500 machines. And for the user, we provide a very nice interface. So the user, it seems to the user that everything is in the main memory of a single machine. So he does not have to worry about where to find its neighbors or how the graph is distributed among so many machines on the cluster. So that's what Trinity is doing.
So to understand, you just said the entire web graph. Like you're talking like a representation of the web and all of its interlinking nodes, feeling as if it is in memory and available to you.
Right.
Like Google or Bing, it's just there and it's instantaneously available.
Right. So, but I'm only talking about the topology of the graph. So I'm only talking about, for example, a web page. It has on average maybe 50 links to other web pages. I'm only, storing the nodes, which is basically a URL, and also its outgoing links in this in the Trinity's memory structure. But the content of a particular web page is not actually stored in memory. They are stored in a database. So only the topology of the graph is in main memory.
Right, and that's why I think that the social networking example is such a good one. On your research site, you give the example that a person, on average, has 120 friends in Facebook. So then if you want to search me, my friends, and my friends' friends, a 3-hop search, while that seems quite easy, it's easy to say, you're looking at 120 plus 120 squared plus 120 cubed. That would be quite an amazing SQL query and no small feat to represent in a traditional object relational database, and you're able to do that in just milliseconds.
Right. So this is actually a very, very important operation on a social network graph. So, for example, if someone searches for something on Bing or on Google, and assuming Bing and Google has the social network information, and then the search engine would like to use the information of your friends, and friends to sort of provide relevance clues to the search. So this operation has to be done in a very, very small amount of time so that the search engine can take that into consideration in, providing answers to the user. So currently Trinity can do that, assuming the data is in, same distribution as the Facebook data. So Trinity can do this 3-hop search within 100 milliseconds. And if you use key value pairs or any other approach, I think the time is actually at least 100 times or even more than what we can do on Trinity.
Hi, this is Scott coming to you from another place and time. Are you using agile practices to manage your software development? There's lots of tools in the market that manage the steps of a project, but most of them focus on individual roles. Get ready for a solution that caters for the success of the whole team. The guys at Telerik introduced Team Pulse. It's an agile project management tool that'll help you gather ideas, estimate, plan, track progress in a common workspace. Finally, companies, regardless of their size, can use a lightweight and convenient tool that makes all the stakeholders work as a united team, even if they're in different countries. By combining intuitive user interface and the power of Silverlight, Team Pulse removes the roadblocks that you typically face in applying agile in an effective manner. No more lost data, no disparate systems, no lack of critical analytics regarding the health and velocity of your project. See for yourself. Get a free copy for 5 users and 1 project at Telerik.com/TeamPulse. And please do thank Telerik for supporting Hansel Minutes on their Facebook fan page, Facebook.com/TELERIK. Telerik. We do appreciate it. There wouldn't be a Hansel Minutes if there wasn't Telerik helping us. Now, a lot of times people accuse Microsoft of reinventing the wheel, although less so with Microsoft Research. Sometimes Microsoft, people say, why don't you use this open source project or why don't you use that open source project? I know that there are other graph databases like Neo4j, and Google has is it Pregel or Pregel? Pregel. So there are other large-scale graph systems out there. What is unique about Trinity vis-a-vis the other examples?
Yeah, so like I mentioned, Trinity is both a online query processing system and also an offline, a batch processing or analytics system. So in this sense, you can think of Trinity as a combination of Neo4j and Pregel. So Pregel is for offline query processing, and Neo4j is for online query processing. But Trinity can provide both capabilities using a single platform. So that's basically the major difference. And also there's another thing which is about the scalability. So we actually have compared with Neo4j when we started this project, and Neo4j is because they have a lot of versions, and we have tried a few of them, and it seems to me they are first of all disk resident, and second of all they are not really very easy to distribute among a set of clusters, among a set of machines in a cluster. So mainly people are using Neo4j for smaller graph applications that can be hosted in one machine. But Neo4j does provide very, very nice user interface and a programming interface to support user application. It's just the scalability that we are trying to improve over Neo4j in that aspect.
I see. And I know that the way that you currently access the data that is inside of Trinity is with a C# API, and most of the samples around asynchrony use that API along with the task parallel library that .NET uses for things like parallel for each. So it seems like you get some free multi-threadedness with the parallel libraries. Do you do additional things within your own libraries to utilize the processors as efficiently as possible?
Yes, we actually did a lot of low-level, hacking in order to support more parallel, in order to have more parallel capabilities. But in our latest release, we actually wrap everything, all those, parallel computing capabilities. We wrap it into the APIs, so the user actually does not have to deal with, this explicitly deal with those parallel constructs. He can just submit his queries as if we are just running on a single machine with a single thread, and the system will automatically take care of that and parallelize its computation.
Interesting. So the data could be across one machine or hundreds and hundreds of machines. It could be across 400 processors or 400 times 24 processors, and they don't have to think about it. It's as if they're dealing with an in-memory structure themselves.
Yes, exactly.
Well, that's a very comfortable interface. That seems very pleasant. Is it always going to be C# though?
Yes, currently we only provide a C# interface, but of course, I mean, in the future we can look into possibilities of providing another kind of another interface, like for other programming languages and other interface.
But what about a DSL? What about a domain-specific language or query language? Is there a standard around graph databases as there is around object relational database?
That's a very good question. Actually, we don't have anything like that right now. Although we have a side project which is, using Trinity as a platform, and we are building an RDF data store upon Trinity. And for that project, we have the traditional Sparkle as a query language to query the RDF data. But of course, I mean, Sparkle is quite limited. The expressive power of Sparkle is quite limited. It's okay for very standard RDF queries, but a lot of graph operations cannot be expressed using Sparkle. But at this moment, we actually don't have a domain-specific language for querying graph data. And it is actually one of our research focus, and we're thinking about designing more flexible query platform, programming platform for graph data. But on the other hand, we do have programming module which is close to Pragio implemented in Google. So, for example, the users will just write a very, very simple script for specifying what kind of things a single node will do in each round of computation. Like, it will accept some messages from its neighbors and perform some actions on its messages, and then send out messages to its neighbors. So the users will just provide a script to describe this kind of actions, and the system will take care of their parallel execution. So this is how the offline analytics is being implemented in Trinity. Of course, this is just one scenario, and the other scenario, for example, we also provide breadth-first search. And as we, go into every node during the breadth-first search, and then we will execute scripts specified by the user on each node. That's another programming model.
Do you see graph databases being something that the average person's going to know about? Like I wouldn't have said 5 years ago or 10 years ago that there would be much interest in document databases, but they seem to have really come of age the last few years. We've got object relational databases. There were, in fact, a lot of object-oriented databases over the last 20 years, although I don't think they've necessarily broken into the mainstream. Is graph data something that will be kind of obscure and on the edge, or do you think it'll be something that the average programmer will be using in 5 or 10 years?
I think there's a possibility that the graph is going to be adopted as a major, even most important data structure in our future applications. So if you think about it, I mean, the data is getting more and more complex, and if the complexity of data is, is very limited, and the size of the data is also limited, then we can very comfortably use relational database like SQL Server to provide, support for these kind of applications. But the reality is, data is getting more and more complex in almost every domain, in search, in scientific computing, for example, bioinformatics, and in, social networks and everything. Data is getting more and more complex, and you cannot use, tables to represent those data, and hope you will have model the data very, very nicely. And on the other hand, of course, the size of the data is getting bigger and bigger. So this is actually opens up a huge space which traditional database cannot serve because they are only good for small data and not that complex data. And graph data will be a very important player in this very, very big space. A lot of applications will rely on graph data. And we actually have got recently many requests about what Trinity can do for some specific applications in game domain, in scientific computing, in bio applications, and things like that. So I can foresee many interesting applications that will require very, very flexible system that can support graph data.
What do you think about some of the newer graph data? I wouldn't say necessarily formal databases, but implementations of graph-like databases using distributed memory structures, like, for example, Redis graph and some naive implementations of a social graph using Redis, FlockDB, what Twitter used for their graph database. Do you think that these are fully fledged graph databases that could compete, or are these just naive implementations over a standard distributed in-memory data structure?
I think they can support certain kind of graph operations, but definitely not all range of graph operations. So, for example, in many social networks, including Facebook, really, the users does not have the power to actually go through the huge social network graph to find information of his neighbors and the neighbors' neighbors and so on and so forth. What social network, what Facebook provides on their website is basically when a user logs in, it provides information about his friends, his direct friends. So there's really just one step, multiple hops on this huge graph. So if this is the case, then key value pair is a very, very nice solution. So the key value pairs will provide the information you can think of it as providing information of it for its direct neighbors. But as graph operations get more complex, and some applications, usually analytics applications that require exploring this graph database, exploring this huge graph along those passes and in a very large scale, then those key value pair store will not function very well. So because fundamentally they still require a lot of joins, a lot of index for exploration, for going from one node to the other nodes. So that's the fundamental problem with those kind of approaches.
And in conclusion, where do you see your project going? Is it always the goal of a researcher to get a project to become a product, or is it simply your goal to expand the knowledge in the space and leave it up to the product people to figure out if they'll sell it or not?
So we are, of course, we are still a research prototype, but we are actually working with a few product teams within Microsoft to support their applications. So, for example, we have within Microsoft, we are dealing with the web graph. We are dealing with the search log and the query graph, and we are dealing with the social graph. So we are working with the product team to use Trinity to support those kind of applications. And as our vision is to provide a general purpose graph computation platform. So using these applications, we are basically trying to see what is the priority for improving our system, and eventually we would like to provide this system as a general purpose system for a new kind of data, which is the graph data.
Actually, one last question, just to get a sense of size, so the listeners who are going to go off and research this themselves and learn more about your stuff can understand. I know that as of mid 2010, Twitter's graph data called FlockDB had about 13 billion edges, and they were doing traffic of about 20,000 writes a second and 100,000 reads a second. So about 13 billion edges, and I'm sure they've increased since that. Do you have a sense of how big Trinity can get?
We haven't tried. We're still working with the product team to try, to use Trinity for the web graph. So we're still in the process of it. But 13 billion edges is actually not that big. So because, for example, we are dealing with the web graph, which has, for example, 200 billion nodes, and for each node is basically a web page, and each node on average will have 40 to 50 edges. So if you times these two together, then it is much bigger than a social graph. So basically, web graph is still the largest graph on the earth. I mean, a man-made graph on the earth. It's much, much larger than the social graph. So we are trying to use Trinity to support that. Wow.
That's really comforting to know that you can think about edges in the terms of billions and billions and not think of it as being too large. That speaks really well for the work that you guys are doing. Well, thanks so much for chatting with me today. I really appreciate it, and giving people outside the research community an opportunity to learn more about what you're doing in Microsoft Research.
Thanks for having me.
This has been another episode of Hansel Minutes. Big thanks to Haixun Wang and the folks at Microsoft Research Asia. We will see you again next week.